So what I will present today is actually an ongoing study that the untargeted approaches help us actually to identify hidden problem we have in Nueces Bay, and it's due to the petroleum brine that was released in the bay. So a little bit background about the petroleum brine. Petroleum brine is, as you know, Texas is one of the main producer of petroleum, and you can find these along the way almost everywhere. So from 1900 until now, there was a lot of petroleum exploration. So when they drill the wells, you will have oil in the middle, and you have the gas in the top layer, and you have water. And this water is normally brine, and it has a lot of salt. So normally, sometimes they draw, not sometimes, most of the time, they draw 3 wells, one to get the gas, and one to get the oil, and one to get the brine water. That brine water, what they do with it, they throw it on the coastal area, and it was allowed to do that. It was permitted from 1900 to 1993 when it is stopped. For example, in 1979, it was estimated that there are over 32 million gallons of petroleum brine was discharged daily. Every day, there are 32 million gallons of this petroleum brine. As you can see, the petroleum brine is not only pure water. It is in direct contact with the petroleum. So it's contain a lot of hydrocarbon. And that was dumped on the tidal water. One of the big issues, so there are many studies that are trying to understand, okay, what is the effect, what is the environmental effect of the petroleum brine? And they find it is very toxic. Especially they find, for example, there are studies showing this bird, which is the western sandpiper, it is very high toxic, and a lot of it is, they find when they go to the stomach, they find high petroleum hydrocarbon inside the stomach because the way it is eating. And also the Eastern American oyster, they find really high petroleum hydrocarbon, especially in the area where they discharge the petroleum brine water. And because of all this study and all that concern, in 1993, discharging of petroleum brine is stopped. So it's almost now 24 years, and there are no petroleum brine discharged in the coastal area in Texas. One of the area that impacted a lot, was Nueces Bay. I'm not talking here about petroleum. This is not for a petroleum problem. It is indirect effect of the petroleum brine, as I will show you later on. And we will not see the indirect effect actually until, the only reason we saw it and we identify it is because we used the untargeted approach with the high resolution mass spec. So Nueces Bay, it is a secondary bay. There are Corpus Christi Bay here, which is connected to the Gulf of Mexico, and there are Nueces Bay. Here it is a secondary bay, and there are Nueces River. And in the northern side, that's most of the petroleum brine have all these yellow dots or triangles is identified as petroleum discharge. So these all was petroleum discharge until 1993. One thing you need to notice is actually this area where it is the petroleum brine was discharged was agriculture region for a long period of time. With agriculture, as you know, there are a lot of pesticides and insecticides that we've been used. So the connection between the agriculture region and the petroleum brine, that's what will cause this problem, what we will see now. So Nueces Bay, unfortunately now, it is suffering a lot of troubles. Even though the petroleum brine is stopped, but they attributed a lot of the unduned marshes. They cannot grow anything, and also, so the unduned marshes, and also they could not grow any oyster back. So all the oyster industry here, it is done, it's gone, even though it is 24 years. One issue with the petroleum brine is petroleum hydrocarbon, yes, but the other thing with it is really high content of iron. So as they discharging petroleum brine, they discharge also a lot of iron, and they deposit on the bay itself. So keep that in mind. So these two pictures was taken in 1990 and showing almost, I don't know if you see it from there, but it's almost red water. It is really full of iron, and that was discharged to the bay. So the bays, as I said, it suffer a lot. And even though it is stopped, the petroleum brine from 1993, there are no more discharge of petroleum brine, but still now we cannot grow any oyster in the bay. So we said, okay, let's try to find what's the problem now. We know there are no petroleum brine anymore. There are no oil discharge. So what is the problem? It is 24 years, and we still have a problem with the bay. We cannot see anything. So what we did is we did some sampling. We have two transects. One it is the northern transect, and one is the southern transect. The northern transect, we could not reach to this area because it's very shallow, and it is very muddy, so we could not sample any water from this region. So we have the northern transect from 1 to 7 stations, and we have another southern transect as a comparison from the southern of the bay. And we collect some water from there, and we extract it with this SBE, with the BBL extract. And then we run it with the high resolution fusion Orbitrap. We just got this instrument for 3 months. That's why it is ongoing. The beautiful things about this, the FTICR and the Orbitrap fusion, almost they have the ultimate high resolution, the highest resolution mass spec. For fusion Orbitrap is almost like 500,000 resolution. To give you an example why we care about resolution, especially for untargeted, this is exactly the same samples. This running by QTOF, and see here, it is from 635 mass Dalton to 635.4, so it is only 0.4 Dalton. And see this bulb here by the QTOF. But with the fusion and FTICRMS, exactly the same sample and the same mass range. So it's actually, this is not a single compound. It is a mixture of compounds. Each peak here, it is a single compound, and this is a full scan. And so with the QTOF, you cannot see this, but with the fusion Orbitrap or using FTICR, will show you all this resolution. So this is a beautiful thing for untargeted. So you will see more compound and try to identify them. So this is a run showing all, it is singly charged, and most of these compounds, we detect them with the high resolution from 200 all the way to 700 Dalton. And look to the resolution here. This is like 0.4 Dalton. It's phenomenal resolution. Because of this phenomenal resolution and the accuracy up to 5 decimal places, we can identify the exact molecular formula. And the error is almost always, it is below 1 ppm. So from this, so we can detect, for example, this compound, it is sulfur compound because it's containing sulfur. This compound, it is phosphorus compound because it's contained phosphorus. If it could not contain phosphorus or sulfur or nitrogen or the heteroatom, we call it CHO. One thing, as you will see, is very handy from getting a list of high resolution mass and exact molecular formula without doing any MS. We can calculate O to C to H to C. So in this case, O to C, what I mean by is how many atom of oxygen divided by how many atom of carbon. So it is 4 divided by 7 is giving me 0.57. And for the same compound, we can calculate H to C, which is H plus 1, which is because we calculate the exact mass, so we add hydrogen to it. So it is 10 divided by 7 is not ionized, and it is 1.47. So for every compound, we have 2 parameters, O to C to H to C. And this is really handy. Why? Actually, there are one slide maybe I'm missing. Yeah. Oh, yeah, I will come to that. Okay. So I rearrange it. I apologize for that. But keep in mind the O to C to H to C is very handy. I will come back to this. But let's compare now the northern transect to the southern transect. If we look to the total number of compounds, this is untargeted approach, so I'm looking for everything. any type of molecular formula. So this is all assigned molecular formula. For example, station 1 identified almost 4,071 compound, and then 5,000, so, sorry, 3,006, and then 3,000. But you can see in general the northern transect have higher number of molecular formula than the southern transect. So I'm detecting more compound in the northern transect comparing to the southern transect. So if I'm looking more detail, you remember when I show you this, I said, okay, for every one we can classify them. If they are, I identify them as a CHO compound, that means it contains carbon, hydrogen, and oxygen, that's it, no heteroatom. So if we look into the number of the CHO compound, which is contain only carbon and hydrogen and oxygen, there are no difference between the southern transect and the northern transect in the total number of compound. But when we look to the phosphorus, more phosphorus in the northern transect comparing to the southern transect. Southern transect, this is a general thing. So when we look to the open ocean or anywhere using the same technique, always we detect around 200 phosphorus compound. But here we detect up to 1,000 compound in station 1. That how many organic phosphorus compound. So one way to visualize this is a massive amount of data. So how to visualize it? That's where we use Van Calvin diagram. You remember for every molecular formula we calculate here, we calculate O to C to H to C. That's become handy because we can plot them against each other. So every dot here is represent one formula. So the relationship where you plot them tell us a lot of information. So this is one sample, and every dot is one molecular formula. If it is lipid-like compound, it will plot in that region. That's where it is highly hydrogenated, so it is most of the lipid will plot here. The protein compound the protein and peptide will plot here. Amino sugar will be here. Carbohydrate, tannins, condensed aromatic, if it is highly aromatic, it will plot. So this is very useful plot or representation of all the compound for untargeted approach, because if I put it in this diagram, it can give me some information what type of this compound is. So if it is plot here, that's meaning without doing any MS. This is only based on the molecular formula. I can have a feeling what this compound could be. It could be lipid, it could be condensed aromatic. So it is a useful way to present this. So instead of looking to the number now, let's look to the Van Calvin diagram. This is only CHO. So this is only molecular formula that contain carbon, hydrogen, and oxygen. So this is station 8, which is near the river, and this is station 1. The CHO, the number of compounds is almost equivalent. There are almost like 80 more here, but the distribution, it is different. So we see this, and this region, we detect 83 molecular formula, and this is 26. And this region is so specific, it is only for oxygenated petroleum hydrocarbon. That's where we expected petroleum hydrocarbon. And keep in mind, petroleum hydrocarbon normally is not ionized very well in ESI. This is electrospray ionization, unless it is oxygenated. So these are some of the oxygenated petroleum hydrocarbon. We detect them here, but they are much less is actually here. When we look to the phosphorus, you remember in phosphorus I detect almost 1,000. The phosphorus here is 200, but all plot near the lipid region. While here they have less H to C, that means it is more aromatic characteristic comparing to this. So I'm detecting more compound, but they are not fitting on the aliphatic compound. That's where I expected most of the organophosphorus, the natural organophosphorus, will be plot on the aliphatic region. If we look most of the lipid, most of the organophosphorus is either lipid or associated with peptide, so it will be mostly in this region. But detecting all this compound in this region, the organophosphorus, that's indication that these are not natural organic phosphorus. So if we look more detail, let's look to the northern transect. Station 1, this is CHO compound, carbon, hydrogen, and oxygen compound. So you can see this region, the aromatic hydrocarbon, as we go away from the discharge, it is going down, so it is decreasing. The same thing with the phosphorus. See, we're having more of this, which is outside the aliphatic region, and as we go to station 7, away from near the discharge, it is almost gone. So we try to explain, apologize me, I don't know, trying to explain here, I don't know if you can see this red line. So what is this? This is the sediment. This is the water column, and this is the sediment. When they deposit iron from the petroleum brine, iron have high affinity to absorb any organophosphorus. It is well documented, so it is all the organophosphorus and phosphate will be adsorbed to the iron particle. If it is iron 3, it needs to be iron hydroxide. In a case of iron hydroxide, and it is oxygenated water, so it is most of it will be absorbing all the organophosphorus. So you can imagine in 1990 and before that in 1900, all the pesticide that was used on the agriculture, so it was adsorbed to that iron that we been deposited, and it trapped there. So a lot of these organophosphorus now it's banned, but it is adsorbed to the iron, so it is taking away from the water. However, with the sedimentation, as we go with time, and we having more organic, these compound will be away from the water, from the oxygenated microbe. If they run out of the oxygen, the first thing they will try to use as a source of oxygen to oxidize organic matter is nitrate. Nitrate is low concentration, so it will go fast. Then they start to use iron 3, convert it to iron 2. As they convert iron 3 to iron 2, so you will see an increase in iron 2 solubility, and the organophosphorus start to come out, which could explain. So most of these organophosphorus is not released now. It used to be released maybe in 1900. So this is like a heading problem. From 1900, all that organophosphorus that was used in 1900, 1920, 1930, and it is adsorbed to the petroleum brine iron, now start to come out. And this is a big issue because a lot of this is now banned, but it's being released to the water column in Nueces Bay. So what we are doing right now is, so we went and looked for all the organophosphorus pesticides, and we identify almost 104 known one. So it is like now, after we use the untargeted to identify there are a problem with the organophosphorus, then we said, okay, could we identify any of them? It is ongoing study. So what we will do, what we are doing right now, still we do not have the data because I just have the instrument for 3 months, but I'm using the Fusion Orbitrap. The Fusion Orbitrap, as I said, it is high resolution, 500,000 resolution. But the other interesting thing, it has 2 mass detector. It has the Orbitrap, the high resolution, and it has Ionotrap, and both of them can work simultaneously in the same time. So if I need to, what we can do full scan through the Orbitrap. As we're doing full scan in the Orbitrap, we can fragment some of them. We can select some of these ions and fragment them through the HCD and detect them with the Ionotrap. In the same time, we are detecting a full scan. So it is you can imagine you have 2 mass spec in one shot, in one sample. So one of them is collecting the full scan, and the other one is the Ionotrap is collecting the fragment. And the scan speed for this is 20 hertz. It is 18 hertz. That means I can collect 18 spectra per second. For the Ionotrap, it's 20 hertz. For example, the FTICR mass, even though it is the same resolution as the Fusion Orbitrap, but the scan speed, it is only 1 hertz. So we cannot use HPLC attached to the FTICRMS because it is low scan speed. But with the fusion, it allows us to take a full advantage of the separation with the HPLC and UHPLC and having two mass detector in the same time in the front of the quadrupole, which will do the separation. So what we are ongoing now, so what we will do, we are going to collect some more bore water and sediment, and we're going to map the whole region to identify what is these organophosphorus, and if we can identify their concentration and what they are. And we're trying to identify the solubility of these compounds and how they are diffused into the Nueces Bay. And we hope if we can identify this, we can have an explanation why the ecosystem it is so disturbed. Still, it is 24 years after stopping all the petroleum brine in that region, but still the problem, because we're still producing more organophosphorus, which was hidden until we used the untargeted approach. So in conclusion, the process controlling the northern transect on the Nueces Bay, it's different than the one in the southern transect. And the northern transects show greater anthropogenic influence because of the petroleum brine with the iron that absorbed all the organophosphorus and now started to leach out all the organophosphorus after the change in the oxidation state of the iron. And most of these samples closest to the oil field of brine discharge. Any question?
Okay, I have a question.
Sure.
So does the bay flush? It's open to the ocean, I assume.
Yes, yeah.
So when that iron 2, it's soluble now, it comes to the surface, is that water aerobic or anaerobic?
No, it is anaerobic.
Anaerobic. Doesn't the bay then flush with ocean water to make it aerobic again, or is there so much carbon?
No, because of the sediment, because you have a lot of organic. So the oxygen, if I return back, I don't know if you saw this, but if it is clear. So the oxygen here, it's reach only like 5 centimeters. Because even though you have a lot of oxygen here, because the organic is a lot of organic,
Right.
so it's make it all anaerobic. And most of the iron too that is being dissolved, it will react immediately with sulfide. Because after
Right.
the
Iron
microbe,
sulfide.
they use all the iron 2, they start to use sulfate,
Yep.
to produce H2S, and then H2S will react with iron 2 and make byrite.
Iron sulfide.
Iron sulfide, and it is byrite, and it will precipitate again as a byrite. So the iron will not get a lot of it to the water because of the sulfate, which is the next things. But the organophosphorus, because organophosphorus is so have a strong affinity to bind to iron 3 hydroxide. If it is iron 2, it will release.
Okay.
Exactly. And it's like a hidden bomb there with a timing bomb, you know?
Right.
And we could not see that if we will not use the untargeted approach, because we was looking for everything, and then we said, there are a big difference here.
Yeah.
If we will go, we will never think there are organophosphorus problem, because we know now the agriculture in that area, they are not using any organophosphorus insecticide or pesticide. They stopped using it, but they used to use it in 1920, 1930.
Yeah.
And a lot of these compounds is not banned, but now started to release back.
So what's then the follow-up then? What's the how resilient are they to degradation, the organophosphorus pesticides then?
We need to investigate it further. But one thing I'm looking to is actually the photooxidation. So
Okay.
Because they are hidden here away from the sunlight. Now when they get the water column, they are exposing to sunlight and it is oxygenated. What will happen to them? And that's one thing maybe explain why we see a lot of, or it's like 800 compound.
Yeah.
Could not be 800 pesticide there. So it could be a derivative of these of these pesticide, but most of them are highly aromatic. And we need to put our point on it, because this is a problem that could happen anywhere else. If you have iron and you have organophosphorus, you think you don't have the problem again, but you could actually coming back to you.
Right. Okay, excellent. Thank you. Any final questions? If not, please join me in thanking Dr. Abdullah one more time. And